First of all, I would like to express my gratitude for the honor to be invited lecture for the invited speaker for the introduction of infrared fiber optics. It's really great, for this esteemed conference to show great opportunities how infrared fiber optics can change systems based on lasers, infrared detectors, and used not only in space, used on Earth. I was lucky 40 years ago, starting my diploma and PhD, to be involved in development of mid-infrared fiber optics. Everybody is familiar with silica fibers. It's more than 1 trillion kilometers used for telecom today. But mid-infrared, from 2 to 16 microns, it's relatively rare fiber optics. And I am one of the 3 pioneers, together with my friend Jim Harrington, and from United States, and Abraham Katzer from Tel Aviv University, to start it many years ago. Today, after the academic development, we already reached and we produce in our company, we exist more than 22 years, all type of fiber optic products. But our leading product is mid-infrared fiber optics, chalcogenide fibers for the range 1 to 6 microns, and silver halide polycrystalline fibers, with abbreviation PIR fiber. PIR fiber is polycrystalline, and you can see on electron microscope photo how small is the grain structure. It's not a glass, it's really grains with an average size from tens to 100 nanometers. And these fibers are extremely flexible. And I would like to show you how flexible they are. Because you can really bend them in small radius, and you can even do something which is almost impossible with any other fiber. You can make a knot based on this fiber, and it's really tough to stretch them, to break them. We developed this fiber even for special application in space. It was a great program named Darwin Mission of European Space Agency, with very ambitious wish to find exoplanets using Nulin interferometers and analysis in mid-infrared for the atmosphere of these exoplanets. We did it with our great partner company Astrium in Germany. And our single mode fibers have appeared after 2-3 years of development, something like half a year ahead of our competitors. That time it was Abraham Katzer doing it with NASA. So that's why we are proud to make the first single mode fiber in mid-infrared. Today, we have new partners in America with fantastic opportunity to do experiments even in space. So over here at this slide, you see kind of special chamber where it was already great attempt, to draw fluoride glass fiber. And now this opportunity exists for international community, for scientists from America, Russia, China, and so on. Fiber, mid-infrared fiber, has unique transmission. So everybody familiar with this kind of nice instrument to measure temperature. But this is only by external or direct view to the elbow or to the hand. While if it will be coupled with infrared fiber, it can be used even inside human body. So it will be infrared endoscope. In this case, of course, fiber should be coupled with infrared detectors. And these detectors can be bolometer, can be thermoelectrically cooled MCT detectors, or even liquid nitrogen cooled MCT detectors. Then it will be detection of temperature with a precision of, let's say, 0.1 degrees Celsius For infrared endoscope, it was great development done by company Securus, and later on Boston Scientific. From the left side, you see infrared fiber bundle, which is used for infrared image transfer. And this is also possible for any application in space, not only for medical, it can be also for the radar or detection of infrared moving objects applications. There is one type of flexible cables based on hollow waveguides, which is different from chalcogenide glass fiber or polycrystalline fiber. And this is based on capillary, silica capillary with internal coating by silver and silver iodide. It was developed by my excellent friend, Professor Jim Harrington in Rutgers University, and then licensed to company Polymicro. There are more manufacturers today, company Guiding Photonics in California and others. So you can see that by variation of thickness for the silver or silver iodide, you can move, you can shift transmission band of these hollow waveguides. Either it's close to 10 microns for CO2 laser or to carbon monoxide laser for 5 microns. Comparison of hollow waveguides and polycrystalline fibers is with some advantages. It's a smaller optical losses in polycrystalline fiber with a large numerical aperture, while hollow waveguides are good for transmission of power from lasers. And you can see, for example, examples with CO2, medical CO2 laser or carbon monoxide laser, in this case from coherent, where the coupling into the hollow waveguide will be even better than with pure fiber, because with pure fiber we have refractive index more than 2 and Fresnel losses at every end, so which is altogether more than 30%. We suppress these losses by very special technology of microstructuring of fiber ends, but it's only, how to say, partial solution. Nevertheless, for the bending, there are advantages of polycrystalline fibers because they are very stable even for the radius like this. For hollow waveguides, this radius will reduce dramatically transmission of hollow waveguides. Even for relatively large radius like this, it will be about 15% lost. I really would like to direct attention to a great market which is fast growing on the planet right now, biophotonics. And if you will compare different areas, different segments, defense, advanced manufacturing, energy, lighting, then even with information technology, which is about 23% of the total investment from private investors in the world, biophotonics is leading. It's almost 30%. And reason is very simple. Everybody would like to live longer, to be healthy, and to be young even when you are 100 years old. So with this kind of great purpose, we really invest more in diagnostics. You see that diagnostics in 25 will be really dominating investment for the medical application, while treatment itself will be maybe about 40% only. One of the methods of diagnostics will be measurement of, let's say, parameters, molecular composition of tissue. In this case, on this slide, you see that we have a project with 12 partners in Europe named Miracle to detect disease of cartilage, so meniscus of the knee. And the box on the photo, it's 7 quantum cascade lasers united, combined by bundle of pure fibers into one fiber, and then arthroscope simply measures the spectra and bring with one fiber signal back to the system. So then we can distinguish disease from the normal tissue of cartilage. But as soon quantum cascade lasers are really fantastic, working at room temperature with extremely narrow line width, then it's possible to measure gas phases. So in diagnostics, it can be, for example, measurement of exhalation, because in our exhalation we have from 600 up to 1000 volatile components, molecules, and there are some specific absorption or let's say molecule which is specific for diabetes. Ammonia, you see that exhalation of diabetica is really specific. You can detect it. And this is possible with quantum cascade lasers, especially when they are so easy assembled with fiber optics like that. And even for the narrow tunability of one laser, you can use several of them and make a fiber optic bunch, for the collection kind of Lego system, to select appropriate lasers. This is even applicable for COVID diagnostics. There are already great work done in Ohio University for diagnostics with electronic nose. There is interesting analyzer for gas analysis, for exhalation analysis developed in Siberia by Russian scientists. And quantum cascade laser can provide very good solution for this big problem, because COVID will not disappear tomorrow. It will not disappear even next year. So at the end, I would like just to attract attention that same infrared fiber is great for any infrared spectrometer. Most popular is FTIR spectrometers, and this is good to measure any kind of composition, any liquid composition, molecular composition, and tissue as well. We decided to invest. Within the last 5 years, we invest a lot in diagnostics of the border for tumor, because when surgeon tried to excise it, to remove it completely, he never knows, where is the border. That's why there are too many mistakes, and this disease is much more, deadly compared to COVID. If you will see the statistics on the slide, every 4 seconds we lose one person on the earth because of cancer. That's why if we are able to make a better treatment, better diagnostics, we can reduce number of people dead because of cancer. So we tried to do it, to develop it with fiber optic probes, and with our partners at Charité Clinic in Berlin, when we used 2 methods together, fluorescence and mid-infrared absorption. When we fuse data from these methods, we really increase precision of detection for 3 to 5 times. And it helps to the doctors really to make complete removal of cancer with a better lifetime quality after and longer life after the operations. Not only research with different spectrometers, we even develop a prototype of small device where the whole spectrometer was replaced only by 4 LED and 1 photodiode. And this particular sensor was really good to detect so-called renal cell carcinoma, cancer of kidney. You see this kind of red and green diagrams. You can see that it's possible to differentiate tumor, non-tumor with a simple device which data goes to cloud and can be really in real time treated. So doctor will simply have only red or green light or special sound when he will detect borders of and tissue to remove tumor completely. With this kind of approach, not only LED, not only quantum cascade lasers, there are so-called MEMS, infrared tunable filters, which are produced by several companies like Infratech, for example, in Germany, in Dresden. And with them, it's also possible to make fiber optic sensors. So it's good for liquids, and it opens the whole horizon of the future for the whole family of very different specific medical sensors for diagnostics, or it can be special sensors to detect quality of food, quality of meat, quality of milk, and also for industrial use, even for space. Analysis of combustion process is possible inline. Analysis of fuel used for engine is also possible inline. in real time, and we are really happy, how to say, to look for the great future of infrared fiber optics in fusion with great partners making detectors, lasers, spectrometers. So that's why at the end I really would like to say that probably we shall create a new family of Internet of Things, which will be spectral fiber sensors for very different applications. And of course, it's impossible without collaboration. And I hope this conference will bring interesting connections. And you can see from this last photo that not only, let's say, inline control of anything which is going on planet or in space is possible, collaboration. We really need, let's say, more than one partner to make great things. Thank you for your attention.